Ah bon? Ah là oui, pardon. Je suis pas là.
Good morning.
Hey.
Hi, Théo, can you hear me?
Yeah, I can hear you.
Hello.
Hello.
1, 2, 3.
Okay. Mm-hmm. Mm-hmm.
Oh, also. Hello, Shisha.
Hello, Hendrik.
Oh, wait, maybe it's me.
Okay.
Hmm. Test. Hmm.
Hi, Hendrik. What's wrong?
No, I can hear you. At the
Okay.
beginning, I couldn't hear you. Good to see you, by
Okay.
the way.
Good to see you again. I remember you also attended the thesis presentation of Thomas Ertel's Johanni's thesis presentation.
Yes, yeah. So, hanging around here in Europe. Oh, hey, Roma. You look so formal today. Maybe
because this is a big day for Roman.
Normally the candidate should always be better dressed in jury, and I always participate in this effort. So Omar didn't. Okay, can you guys hear us?
Yep.
Yeah.
Okay. Good morning, everyone. Thanks for taking part to this PhD defense. Before starting, I would like to introduce first the jury members. We have Céline Udreau, professor at Centrale Supélec, and David Aubert, professor at University of Bordeaux. We have also Professor Liu Shixia from Tsinghua University, Dr. Hendrik Trovert, researcher at IBM Research Watson AI Lab. We have Christian Webb. He is the supervisor of this thesis, and Dr. Romain Villemot, associate professor at École Centrale de Lyon, co-supervisor of this thesis, and I'm Ning Chen, professor at École Centrale de Lyon. I'm chairing this PhD defense. So Théo is presenting his thesis work entitled Deep Learning Interpretability with Visual Analytics, Exploring Reasoning and Bias Exploration. You're going to have 45 minutes for presentation. Then the jury member are going to formulate questions. Okay. So now it's what, 10 minutes? Yeah, 3 minutes. So you are having 45 minutes. You've got the floor, please. Yeah.
Thank you. Well, thank you, Lenin, for this introduction, and welcome everyone to my PhD defense entitled Deep Learning Interpretability with Visual Analytics, Exploring Reasoning and Bias Exploitation. When I was 2 years old, Garry Kasparov became the first world chess champion to ever lose a match against an artificial player. Back then, such a news hit as a revelation that in the next few years, machine learning will be everywhere in our lives. Nowadays, 2 decades later, I'm sure we all have this piece of technology in our pockets. For example, to look for it in an itinerary, to be here today on this phone, recommendations and social medias, and even autocorrection of our typing. But among this application of artificial intelligence, we still are missing robots doing our housework and autonomous cars traveling us around. This can be explained with this illustrative case. Let's say that we have an autonomous car that drives past a stop sign, and we want to ask why did this happen? How the crash occurred? What we want to do is to understand how the car missed the stop sign and who might be responsible for such a crash. Answering these kind of questions is what we wanted to explore during my PhD. And more precisely, we focused on interpreting deep neural networks to assess their biases and reasoning capabilities to identify the sources of their mistake and eventually prevent them. But first, how can a deep neural network learn to detect a stop sign? This kind of model first need to digest a large amount of data. And we take the data and give that to the model, which is then asked to output prediction of stop traffic signs or speed limit runs. because this is the first time that this kind of model I've seen these pictures, it will make a lot of mistakes, which is good news because we can use these mistakes to produce gradients that we can use to update the model and make it better. We repeat this operation until the model is good enough, or at least we consider that the model is good enough to deploy into the real world. Such an approach has issues because it cannot cover every situation that the real world possesses. For example, here, if we just provide a few patches of duct tape on the stop traffic sign, we can change its prediction from a stop traffic sign to a speed limit one, hence perhaps the cause of the traffic. Analyzing what's going on inside of these models and how such duct tape may cause such issues is what we want to do in visualize and understand this operation inside of the models. This is something that the community has addressed for the last decade. In what follows, I will show you two building blocks of interoperability. First, we have activations, and then we have gradients, which are different from what's the one we use during training, because here we focus on the trained model. Activations are intermediate results throughout the model. Here, for example, we have a model trained to classify handwritten digits. Here we have an image of a 2 and a prediction being 2. And what we want to look at are these images at the bottom of the screen. And on the left side, we have the images that are the first layer of the model that correspond to the prediction. We have these images at the bottom that are quite similar to the input. But the more we go through deep neural network layers, the more they became abstract and hard to understand. And therefore, the community started to combine them with what we can make sense of, which is the input and the output of the model. For example, here, we take our training dataset and give that to the model and collect for each neuron which image will yield the maximum activations. This is what we can see here. For example, on the first row, we have the most 10 images that yield the most intense activations for a selected neuron. Here we can see that this neuron in particular might be sensitive to circular patterns, such as dogs' eyes and snouts. But this can also be applied to text. Here we have a model trained to predict the next character in a sentence. And the sentence being smile are merely meant to say that the Y is missing, and we want to understand how the model is able to predict this Y. What we can do is collect activations for the model as soon as it predicts the next character of the sentence and plot that back to the input using color scale. For example, here we have neurons that might be sensitive to quotes because we can see that the word smile is highlighted in red while the rest of the sentence is in blue. Now let's move on to gradients with this example of a model trained to classify images of animals. Here we have an image of a dog and the good being a dog. What we want to do is visualize how the model is able to predict a dog and if it can do so using the right reasons, so by looking at the dog. What we can do is use gradients different from training. Here we derive the output with respect to the input to highlight which regions of the image the model is most sensitive to. And here, if you can see through these gray patches, you can see that this the dog space is highlighted. We can combine that with activations to provide a more clearer heat map, as you can see here, of what part of the image the model focuses on. And here we see the dog space, which is good news because this indicates that indeed the model is able to look at the right objects in images to predict its output. Finally, the last gradient building blocks using gradients that we'll see today is how we can maximize an image based on the neural activation. Here, we take an image with random noises inside, and we give that to the model, and we derive the neural activation with respect to the input. What that gives us is a gradient that we can use to modify the image and repeat this operation until we have a clear view of what the neuron is looking for in an image. And this results in this kind of fabric or nodding diagram shape. This is the texture that this particular neuron is looking for in images. But throughout everything we just saw here on these building blocks, there is a step that requires the selection of a neuron. But how can we select a specific neuron to analyze when there is thousands and in some cases millions of them? This is something visual analytics is dedicated to. Visual analytics is a domain that emerged in 2005, which is dedicated to answer research questions involved when we introduce interactivity in visualization for decision protocols. A characteristic of these systems is how they rely on multi-coordinated views to provide in-depth analysis of data and their different assets. This makes visual analytics the perfect candidate to combine building blocks and link them through interactivity to provide in-depth analysis of how a deep neural networks can yield an answer. In what follows, I will show you a few successful examples of how visual analytics systems can be applied to deep neural network interpretability. First, we have scene envies, in which each columns are layers of a model, and each square represents a cluster of neurons. This is a core contribution of this tool, which is how neurons within the same layer can be assimilated together based on similarity of activations and represented with the top K images corresponding to the activations. So, for example, here we have images of vehicles that correspond to what images these neurons must correspond to. These squares are then linked in a log diagram to visualize their contribution toward the model until we reach the output at the end. Such a representation has also been explored using an attribution graph view, which combines what we just saw earlier about the maximization of an image to make it look like what the neuron is looking for in an image. And for example, here we can see how the model relies on hands of fishermen to distinguish between a picture of fishes and a species of fishes. This is due to the fact that in our dataset, we have plenty of examples of people taking pictures of their fishes during a fishing setting, and therefore the model relies on the ends instead of the fish itself, which is a bias we want to tackle. And finally, for text, we have this example of HTMVs, but due to the sequential nature of text, what we want to do is to find correlations between activations and words of a sentence. For example, here in LSTVs, users can select an interval of words, and therefore the system filters activations based on a high activation or high intensity during the selected interval. And then we can find correlations between the line slopes. So here, each line is an activation, and of selection, which then can be further improved with additional information, such as the role of the words in the sentence. For example, if it's a verb or a noun or whatever. During my PhD, we focused on interpreting state-of-the-art deep neural networks to reduce the biases. To do so, we decided to focus on robotic applications, but our contributions are not limited to them and can be used outside of robotics. First, let's take an illustrative case of what we want to do. Let's say it's getting late at the office. I want to go home, but sadly my keys are missing. What I will want to do is ask Moritz, our local robot, to find it for me. But first, we need to train Moritz to tackle several challenges. First, we have perception. Moritz needs to be able to understand what I'm looking for from natural language questions, and then identify this object in pictures. Then we need to train Moritz to navigate in the environment, to explore the rooms and find the skills. And finally, since we train in simulation, we then need to deploy everything we just did on perception and navigation back to Moritz itself, which needs to handle these challenges of an ever-changing real world. For example, if there is open or closed doors, luminosity, this cause issues for Moritz to evolve in this environment. This is done in case of my PhD. These changes of perception, navigation, and sensory have been tackled using visual analytic systems to interpret deep neural networks designed for this kind of tasks which can be extended outside of robotics. So first, we have perception, which was issued from the collaboration with Orange Labs. From these collaborators, we interacted weekly to provide them information of our tool we are designing with them to improve, and they gave us feedback of what they expected to visualize and what they want to visualize. This collaboration yielded two contributions, one in an artificial intelligence and computer vision venue, and another one in visualization. In this part of perception, we focus on visual question answering tasks. In our case, we use that as a proxy task to test the reasoning of models, but it has applications to help people with visual impairments and video description. In such a task, we ask a natural language question with an image. For example, here we ask what is the color of the bananas, and what we want to and what we are expecting is for a model to predict the color yellow by looking at the picture. But what we can see is that in most cases, the model can just understand that we're looking for colors and bananas to put yellow and not even look at the image. This is due to the fact that in 80% of training cases, when we ask the colors and bananas, the answer is yellow. So the model only needs to understand that to provide the correct answer in 80% of the cases. The state of the art model on DQA task and what we focused on in this part is the helix-flat transformer model, which is a model that first needs to decompose the inputs in pieces. So we have tokens for words and bounding boxes for the image. These are then associated in the key core function of transformer models, which is the attention. The attention is how the model decides to focus on the inputs or intermediate results. Such attention is learned directly by the model, and therefore it changes its focus on which part of the image and intermediate results for this part and for the model. If we focus, for example, here on the first row, we have the bounding box corresponding to Sherry, and we can see this sort of distribution which associates the bounding box Sherry with the token for the word what. And if we move on to the second bounding box here, we can see the bounding box corresponding to banana, which is strongly associated with the word banana, with the picky attention. This is what we want to look for, because in our case, we estimate that this is synonym of a good reasoning. Then at the bottom, we have this kind of uniform distribution for the bounding box kiwi, which indicates that this bounding box may not be used in this particular attention map. And therefore, our hypothesis is that experts can be able to find examples of bias exploitation by analyzing these attention maps. And therefore, our goal is to visualize and interpret these attention maps for the model to make sure that we can indeed find example of bias exploitation. But visualizing attention maps raise few challenges. For example, we need to explore hundreds of attention maps for the model. How can we select which one we want to visualize first and which one may be conveying examples of bias or reasoning? Then we need to contextualize what we just saw in an attention map on the rest of the dataset. Is this particular attention maps is behaving that way on this particular instance, or is this the case for the rest of the dataset? Finally, in order to be sure that we're visualizing and interpreting the correct reasoning, we explore how we can generate alternative scenarios, for example, by training attention maps or asking different questions in real time. I will now give you a quick tour of the tool and then go back to explain a bit further what we just saw. Here is the interface of VSQA, a visual analytic systems we designed in collaboration with Orange Labs. In this interface, we have the available questions and image on the left side of the screen, as you can see here. These are then piped in a representation of the model in which each square is an attention map. For now, let's just say that, let's ignore the color and just say that we want to focus on the blue ones, which describe how picky an attention map is. So the blue one indicates the pickiest attention, and therefore what we may want to look at first, because there may be synonym of a good reasoning. And then on the right side of the screen, left side for you, you have this distribution of outputs. And for example, here, with the question, is a knife in the top part of the photo, we can see that the model outputs no. But this is the case for the model that we train and design thanks to Insight game with display. This is an improved model. If I switch back to a lesser model, for example, here, we can see that the output is yes when the control sensor is no, indicating that this model failed. If I want to understand why such output is available, I can look and browse through attention maps, for example, this one, in which I can see, if I zoom in, a strong attention for the word knife here, a strong attention for the word knife here, on many and plenty of bunny boxes, but none corresponding to the word knife. This is due to the fact that the previous model designed to extract bunny boxes from this image to provide to our model we are visualizing now, provided no bunny boxes corresponding to the word knife. Therefore, this model tries to cope with everything it can and associate the word knife with a lot of attention maps throughout bunny box available. Now, if I switch back to the model we improved, here we can see on the same attention map a quite different distribution. Here, instead of associating the word knife with every bunny box available, this model only focuses on 2 bunny boxes, which are named handle, which are the handle of the knife. And therefore, this might be an example of how the model is able to cope with the missing bunny box of the knife to provide the correct answer. Now, let's go back here to what we just saw. So we have a scan of representation of color for attention maps. To do so, we use the distribution of each row of the heat map, and we take the maximal pickiness of the row to represent the global heat map. We take this pickiness, we plug that to a color scale, you can see here, and then we use that for the model and for the visualization system to make sense of what we're seeing. Such color is then used towards other views, for example, here, which is a view for the global dataset. You can see the current value of pickiness for the attention map we are currently visualizing and its distribution towards the dataset. For example, here, we can see how particular here on the top, the pickiness of this attention is compared to the rest of the dataset, indicating that this particular attention map for this particular instance is quite sensitive compared to the rest of the dataset, making it a bit special compared to what the model is used to. We related this system with 6 experts during interviews that lasted in average 2 hours. During this interview, we asked them, we provided to them this modified version of display, in which, as you can see here, we remove the representation of outputs, and we asked them 3 questions. First, will the model predict a correct answer? Just by looking at these attention maps, experts were able to reach an average accuracy of 75%, indicating that indeed such a tool is able to help them analyze whether or not the model is able to predict outputs to the correct answer. If we move on to another question, which is what will be the answer? And this in here we ask the correct word and not whether or not the model is correct. And on this, we have a slight drop with an average accuracy of 61%, which can be explained by the fact that in some cases, experts have issues for wording. For example, they predicted that the output would be a chair when it was in fact a coach. So we have this kind of issues that here are represented with this average accuracy. And finally, we ask them, is the model exploiting a bias? And on this particular question, experts reached an average accuracy of 75%. This confirms that indeed, display is able to help experts analyze the bias exploitation of deep neural networks, in this case, transformer models with attention. And in what follows, I will show you 2 examples of insights and discoveries gained by experts using display. First, when we ask this question, is the person wearing shorts the person being cropped here on the right side of the image, and the ground truth answer being yes. When we look at on the model, and we look at the time attention maps that we looked before during the demo, we can see a strong association with the word pattern and both the boxes corresponding to women. And the same goes for shorts, which indicate a good example of a reasoning and what we want to visualize in every cases in perfect world. And in addition to that, if we prune, so we force the model to have a uniform distribution on these attention maps, we can change the prediction from a yes, which was the correct answer, to a no, so bad answer, indicating that indeed these attention maps play a critical role in the prediction of the output. When you run in this example, when we have both knives and pizzas in the image, and the ground truth being no, because there is no knives in this image, we can see how the model made a mistake here and predicts the output to yes when the ground truth answer was no. When we look at the time attention maps, we can see that there is a strong association with the word pizza and many bunny boxes in the model, but none for the word knife, which is what we want because there is no knife in the picture. But why did the answer still yes then? One way to look at that is to use self-language attention maps. So language attention maps associate language tokens of words from the question with themselves. And we look at the pickiness for the word hand and both, and we try to remove these attention maps. We have an improvement of 10% accuracy for the model on this particular kind of questions. This indicates that the model paid to learn how logical connectors may be able, what they imply in the reasoning, and how what we expect in the results. This indicates that such model needs further training on this kind of questions. And this is good news because this is what our collaborators continue to work on. They did a program supervision to force the model to learn how logical connectors functions and what they imply when they're looking and to answer a question. We also did a follow-up with our collaborators, thanks to insights gained in this way, on how we can help the model cope with noisy inputs because of the bunny boxes being missing. For example, in your case, what we just saw, there was no non-bunny box, so there was a knife, and therefore that may be causing the model to learn noisy reasoning and make mistakes. Okay, so now we just saw how we can train models to have this perception to answer natural language questions and find objects in images. Thanks to that. Now let's move on to navigation and how we can train models to move in our office. This work was done in collaboration with Edouard Béchy. He designed the model that we use in this part and the scenario and the simulators that we are about to explore. So in this particular case, we use a simulator to train models to navigate in the environment. This is due to the fact that the simulators can be way faster than reality because we are not bound to physical limits. We can run in parallel planning examples of trials. In addition to that, the simulators are way safer because in simulator, models cannot fail of stairs and bucket stuff. In what we follows, we will rely on the K item scenario of wisdom in which the agent has to collect 4 items in a specific order. We have a green one, a red one, a gray one, and finally a blue one. If you boil down this task and what is asked for models to do is to use its field of view, to give that to a controller, and the controller needs to output an action that models will do to move on to the next stage. If we look a bit inside of this particular controller, in our case, we use an actor critic model. And here we can see that it's composed in 3 different stages. We have perception, which analyzes the image and extract features. We take that to and give that to memory, which helps the model to avoid to run in circles and come back to the previously explored part of the, for example, a room. And finally, this memory helps the robot decide which action it should do and go back to the first step. And we repeat this operation until the bubble has reached its goal, in case of fetching the keys, for example. What we want to look at here is this memory. Our hypothesis is that such a memory is linked to the robot's action, and therefore, if we can understand what information is stored in this memory, we may be able to understand why the agent decided to move to right or left, or its broad strategy. Analyzing this memory raises few challenges because reinforcement learning has no ground truth, meaning that if we want to visualize why the agent decided to turn left or turn right, we have no ground truth to help us decide if this was a good decision or bad decision. It needs human supervision, and we need to observe the full trajectory and not just one action to decide if it was a good decision. Then we have these memory vectors, which are sequential, meaning that all of them depend from the previous ones. Therefore, analyzing one particular memory vector needs to be contextualized with the rest of the memory vectors to understand which kind of information is stored in them. I will give you now a quick tour of the tool and then come back to what we saw. So this is the interface of GRLV's visual analytic system we designed. And here, let's just focus on this part and what's going to go in the bottom, which is here a representation of the memory. We want to focus on dark orange or blue, which indicates a strong activation. So indicating that this particular row may be conveying a strong information of the agent memory. If we play this tool, we can see how the agent behaves on the top right corner. And what we want to do in this tool is try to contextualize this huge memory vector with what's going on and what we can make sense of. And in our case, this goes with the shape of everything available to us in the simulator. For example, whether or not the agent has a specific item in its field of view. For example, here I can filter the memory to only select time steps in which the agent has the green object in its field of view. I can do the same for the red armor, which is a node item the agent has to collect, which yields these two bundles. Then I can reorder the memory to filter and focus on memory elements, so put them in top, based on how likely they are to be conveying information related to these particular intervals. This yields this memory that I can zoom on to focus on the most sensitive one. Here, what we can see is in the first row, a memory vector in which we can see in blue steps in which the agent has the green armor in its field of view that switch to orange as soon as the agent takes this object. So thanks to such, our hypothesis is that thanks to such memory vector, the agent is able to remember that it has collected the green item to move on to the red one. As you can see, this remains orange until the agent has the red armor in its field of view and switch back to blue then. We evaluated the system with the help of 3 domain experts that in interviews that lasted in average 2 hours. In these evaluations, we wanted to evaluate if experts were able to understand, thanks to GRLVs, how the memory is used by these models trained to retrieve deep reinforcement learning. Such interviews yielded plenty insights, but in the interest of time, I will just showcase you what we just saw, which is how some memory vectors are used as flags to encode which items the agent has already collected. Thanks to that, just by looking as previously analyzed memory vectors, we are able to predict which items the agent has collected and which one it's focused on next. This helps us, for example, notice that in some cases, the agent missed the item it has to collect by moving just close to, and it updates its memory based on him expecting that it has collected such item. And therefore, then move on to collecting the next item, which caused the mistakes because they did not collect the previous one. Okay, so now we are able to answer natural language questions based on images and move on to navigation to explore rooms to reach which this case may be located. Now let's move on to how we can deploy this navigation algorithm back to from simulation to the real world. But first, we have an issue to tackle because simulation and real world are quite different. This work to visualize the differences between simulation and real world was done in collaboration with Guillaume Bonneau, which helped me configure the robot and explore the real world. So as I just mentioned earlier, we have quite differences between simulation and real world, especially if we consider that we rely on the Vision simulator, which is quite unrealistic. So what we did here is design a new simulator, which is made from a 3D scan of our lab, which is City Lab at INSALU. And then we train our agent in the simulation, and we want to deploy it directly on the real world, thanks to Moritz here. But a robot doing random actions can eventually, in an infinite amount of time, can eventually reach its goal. Therefore, to visualize the impact and differences between simulation and real world and how these impact the predictions, what we rely on is a proxy task named ego estimation. In ego estimation, we give to the model an RGB and depth image, and we take that to a regression model which will coordinate an orientation model to pinpoint from which this image in particular was taken from the simulator. In simulation, we reach an average accuracy of 96% of simulation images predicted in less than 50 centimeters to the ground truth, which is good news. But when we deploy that to the real world, we can see here, for example, how the same image sample here is predicted on the middle of the environment, which is an unreachable area and synonym of a really bad mistake. Therefore, here our goal is to visualize how can this be possible, what are the differences between simulation and real world, and to visualize that, we design a new visual analytics system. And a particularity of this system is how we can visualize how these differences can have an impact on model prediction. So this visual analytics system is named Century, and such a system is divided in 3 parts. First, we have a global statistic view, which describes distributions of behavior. For example, here on the bottom, we can see distribution of in which room predictions are. For example, here we can see distribution for the ground truth and the real world, which is quite different. We have the same for orientations, and also we can see a bias in which real world is predicted on a specific direction. Then we have a bird's-eye view of the environment. We display here each mark is the ground truth information, which is color encoded from red to green on how far the simulation prediction in the real world is. Therefore, just by looking at that, you can see here, for example, quite a long red column, which indicates that this particular place of the environment caused mistakes between simulation and the real world. Then we have the first person view, which is described using 3 different methods of heat map. We have GradCam, domain occlusion, and finally feature distance. And each column, so we have a column of simulation and the column of real world. And we have 2 images in these boxes because we have an RGB image and a depth image. In the interest of time, I will just move on to the feature distance, which is one we design. In feature distance, what we want to visualize is changes between simulation and real world. For example, here, ideally, what we want to visualize is how this door is now closed when it was open in simulation, and how this bike appeared in the real world, which was not there in simulation. To do so, we use the same model as before and give to it the same images. We collect embeddings at the end of convolutional networks, and we take this embedding to provide continuous distance between these 2 embeddings. This yields this heat map here that we can use to plot on these images to visualize the differences. A core contribution of our system is how this heat map can then be projected back to the from the first person view to the bird's-eye view to highlight regions of the environment which may cause issues between simulation and real world. This is done using the ground truth and orientation, ground truth coordinates and orientation of the prediction. The distance and position is the image thanks to the depth image, and finally the height ratio and field of view of the camera, which is meta information collected directly from voice. But such a representation of a heat map from the first-person view to the bird eyes can also be done for the complete dataset. This gives us this global heat map over the complete office of our city lab, in which red parts here circled are the most pain points and differences between simulation and the real world, and what we want to focus on first. I will now showcase a few examples of insight we can gain thanks to things like this. So first, we have this representation with the distribution here. Each dot is a real-world prediction, and we can see how these real-world predictions are on the most right half of the environment. And when we look at images, we can see, for example, here that we have quite different luminosity between the simulation and real world. And what Syntheory offer is how to adjust in real time these real-world images to find correlations between, for example, brightness, field size, or white balance, and models prediction. And just by increasing the luminosity by 15%, we can see how the distribution goes from being on the right half of the environment back to a more scattered representation over the complete environment. This indicates that despite best efforts to cope with such luminosity changes using data augmentation, for example, such model is still sensitive to luminosity changes and therefore needs to implement in that way. Then we have a second case study on the layout changes. So for example, we have this bike here in simulation back on the fence, and which is missing on the real world. And what we wanted to explore here, because we can see how this is a pain point in the global heat map, is what happens if we remove this bike in simulation. This was done roughly manually using Blender, and as you can see, after removing this back in simulator and train a new model, we can see here a quite different distribution of pain points with less red square indicating the most problematic areas. This indicates that here, such model also needs further improvements to cope with layout changes and need further work on that point. Now, let's take a step back on what we just saw. During my PhD, I designed 3 visual systems and 2 online explorables, resulting in 6 publications in visualization and machine learning venues. Every work we saw there and the 2 online explorables are available online and are open source. But in the future, I will work to continue my work in 3 different aspects. First, we have scalability. As we can see here, this is the memory, as I just showed you, memory on DRLVs. Here, on the example, in the demo, we have less than 200 time steps. But what happens if we reach a larger number of time steps in an episode? How can we visualize in-time correlation in this memory if this memory grows larger and larger? This is something we want to tackle, and we started to work on it by using, for example, filtering, in which we remove time steps that are not required for visualization. This is this kind of compression of the heat map, which for now is maybe harder to visualize. So this is a work in progress. We want to continue evolve in that way. Finally, if I take this representation of display of the model of the larger transformer models you can load in display in real time, we have this transformer model with 400 attention maps. But even there, this is hard to visualize which attention maps we want to focus on, and we need to cope with that because models keep getting bigger and bigger. And one way to do that is, for example, to rely on aggregation to remove the quantity of attention maps we want to visualize. And here, for example, a block based in similarity, just by a single square to visualize multiple attention maps at once. Then we want to contribute in the evaluation, because during our evaluation of this query of how we can remove the input and ask experts to predict the bias exploitation, the correct or wrong answers are positives that we want to share with the community. And therefore, we want to contribute in different positives and continue on that way. First, we want, as I just mentioned, ask experts to predict model outputs, like we just did in this case. Then we want them to guess the inputs directly from the feature. So instead of hiding the outputs, we hide inputs to try to visualize if experts are able to predict which inputs were provided. Then we can remove directly the input and ask experts to visualize which features will be the most relevant from the input and directly from the intermediate results of the model. These kind of contributions and evaluation, we want to conduct large scales to provide more in-depth statistics of how our visuality systems can be able to provide in-depth information of the behavior of the model. Then finally, we want to move on to sharing to make interoperability a more common practice. First, this goes by experts, the target audience of our systems. This goes by making visuality systems open source and accessible online. This is what I concentrated a lot of time during my PhD on. And then we want to generalize these models, these systems to other datasets and models. Because if we want experts to use these kind of systems on the daily basis, these experts need to have a way to quickly deploy their models and datasets back to our systems. In a perfect world, this goes by just dragging their model or dragging their dataset, but we are not there yet. And finally, nowadays in the community, we have this trend of relying on foundation models, which are general purpose models trained without a specific task. For example, we have GPT-3 that is trained to predict the next character of a sentence, then trained to answer questions, and so on. These kind of models, without a general purpose, are then deployed in real-world applications with fine-tuning on a specific task. But how can we visualize and be sure that our foundation model, trained with general purpose, is not conveying any bias and any issues when deployed to the real life with a fine-tuning? And this is something we want to address. And finally, for non-experts, we also want to share insights thanks to visualization systems. This goes by the design of new visualization. For example, interactive blobs. This is something I did during my PhD with limited exploration on visualization systems and rely on highly interactive systems. So non-expert users can try their way to grasp an understanding based on fine-tuning and modifying everything. Finally, one thing we want to work on is how we can export insights gained from our visualization systems into a sort of a print function that we can deploy to communicate insights quickly. And this can be done using our visualization systems and to transform this kind of insight in more readable visualization. This concludes my talk. Thank you for your attention.
Okay, thanks very much.